right, and hi, Youxiang. All right, welcome back to another episode of Pollys Introduction to Computer Networks. And hi, Yuqi. Good. So the announcements this week, I think it's all about the assignments. So we do have PA8, and we also have 4 quizzes due in this week. All right, good. So why don't we go ahead and start? Before we start, hi, Leon. Hi, Xiaobai. So the first topic today is actually something related to what we've talked about already last Thursday. We talked about hierarchical routing. So if you guys recall the IPv4 address space, right? It's a sequence of bits, 32 of them to be exact. And to show it, okay, to the public, to human beings, we turn 8 bits, okay, and convert that 8 bits of binary to decimal. And so in the end, you see kind of 4 numbers separated by 3 dots. Okay, but if you think back to its original form, 32 bits of binary numbers. So in distributing these numbers to machines, it's quite convenient in a way that so if a network admin is given an IP address space that uses 22 bits being the same, the first 22 bits being the same, then in this case you have 10 bits that are flexible that you can assign to individual hosts. Okay, so such an address space you can also easily divide it, for example, into 4 groups. If you extend the network part to 24 bits, right, then you will have 4 of these 24-bit prefix subnets. Okay. So similarly, you can divide the address space of a 24-bit prefix subnet further. So in a way, IP address space there is hierarchical. Higher level organization, and you can easily split it into 4 parts, 8 parts, 16 parts. And that actually suggests also that you can do hierarchical routing. So the last video last week is actually to tell you a little bit about routing. So essentially the spirit is that there are many destinations out on the internet. And each of these destinations is like a network. And each has its own network address. Okay. So you see that 8 of these organizations, they can actually aggregate the address space when they are announcing their existence. So at the destination, you send some sort of advertisements to tell people that, hey, this address space exists on the internet, so feel free to send data over to this address space. And as these address space can aggregate, right? So if 4 subnets, there are 4 subnets, you can actually aggregate it to a 22 bits, okay? 24 bits subnets, you can aggregate 4 of them to 22 bit subnet. And so the advertisements can be concise. Instead of sending 4 separate, okay, advertisements, you can send just 1. Okay. So in hierarchical routing, using such an hierarchical address space, you get to also save the amount of advertisements you send. All right. And the remaining video today is to tell you a special case. In case these 4 organizations or 8 organizations, if one of them needs to move away from this big subnet to another subnet, that hierarchical routing, okay, sending of the advertisements, aggregation of the advertisements will still work. Okay, so let's check that video out. So the slide here is actually introducing a very interesting scenario. Okay, organization 1 originally here is moved down here to a different ISP. So that prefix advertisement will travel down this way, and ISPRS will try to aggregate it with the original IP address block. Well, ISPRS will find that unfortunately the 2 of them are not aggregatable. In this case, 2 separate advertisements will go on out, okay, into the internet. The forwarding table here will contain 2 entries. One is starting with 199, and one starts 200. Something, 18.0, and 23 bits. This one is 16 bits. And of course, this entry here, okay, will arrive also at the router here at the internet, on the internet. And therefore you have 200 something, 16, and 20 here. So this entry is gonna take the packet out this interface. These two entries is gonna take packet out here. So if there is a packet coming in that is supposed to go to organization 0, it's gonna match the first entry, isn't it? Okay. It's not gonna match the entry number 3 because hey, this address space and this address space, they are actually disjoint. Okay, so not gonna match this guy here. So packet going for destination organization 0 is gonna go down and travel and down to organization 0. So setting up the forwarding table this way, not a problem. Similarly for organization 2 and 3 and all the way to 7. Okay, as long as the destination IP address is matching this, it's gonna come down this way. Yeah, I know you're thinking, hey, what if the packet is going for organization 1? You're right, it's gonna match the first entry. Ooh, a bit worrisome, yes. But if you look down the table, right, hey, it's gonna also match entry number 3. Now, if we call back in section 4.2, what did we say? We're actually not just doing prefix matching, we are doing what? Longest prefix match. So which one is the longer prefix? 20 versus 23. So packet carrying destination for organization 1's machine is going to come down this way here and eventually reaching organization 1. So we're okay, right? So the overhead of sending the advertisements is still very low. Now slightly higher here if it's not exactly aggregatable, but forwarding is going to be fine. And we allow what? Organizations moving from one ISP to another ISP without changing the physical IP addresses. Okay? Therefore, all these servers are running here. They can stay using the same IP address without needing to change the name to IP address mapping. Now, we get the block of IP addresses from our ISP, but next question to ask. How does the ISP get its own block of IP addresses? So it's like saying, hey, the system admin asks the higher level system admin, but higher level system admin asks the even higher level system admin, right? And this goes on. Who's the highest level system admin? Where's the end? Yeah, this organization is the end. So ICANN here is the highest level system admin. This is a non-profit organization overlooking, okay, the allocation of the IP addresses, the allocations of the domain names, and managing also the domain name servers. So very important organization. We normally don't know. Okay, only the people who knows about the internet knows a little bit about ICANN. All right, so that was the last bit of IPv4 addressing, and the new topic today, NAT. Okay, so first video is to introduce why do we need NAT. NAT, the Network Address Translation Service. This is one of the most used protocols on the internet these days. It's here to address a very serious problem. We're running out of IP address space. Yeah, 2 to the power of 32, it sounds like a high number, but we do have a lot more hosts, a lot more router with network interfaces requiring these IP addresses. Therefore, IP addresses is a scarce resource on the internet. To get one, you pay quite a bit of money. This is also why, okay, if this is home network here behind the local network, your deal with the ISP is often this. You pay a specific amount of money monthly. You get a certain downlink bandwidth, certain uplink bandwidth, and a certain number of IP addresses. Usually you get one static IP address or 4 dynamic ones. Okay? If you pay more, maybe 8 dynamic ones. But essentially, the more IP addresses you need being allocated from the ISP, the more money you pay. So it's not like every family can afford paying that much. So to try to save money, this is what we often do at home. Okay? We just, subscribe for one IP address. And then we create a home network, okay, using some fake IP addresses that we make up, and a subnet address that we make up. So instead of asking the ISP, okay, asking the system admin for a block of IP addresses, we can afford it. We use fake, okay, block of IP addresses. So we call this local network or home network. Each of the machine, each of the interface is assigned an IP address on the fake subnet. Okay, so these are then fake IP addresses. Now, as long as we are sending data within ourselves, should be fine. But if we want to send data out, wow,
we need to be careful. And that's when we need a NAT server here at the home gateway. So NAT is sitting right here. So all packets that's leaving the local network needs to be using the real IP address, the IP address assigned by the ISP. Otherwise, it's going to be dropped, okay, at the ISP. So now if this guy has a connection to go out, and this guy has a connection to go out, and this guy has a connection to go out, yeah, each of these connections to not collide to each other will be assigned a new port number as well here, okay, a different source port number. Source IP address changed to the global IP, the real IP, and the port number changed to a different number so that they don't collide to each other. So that is the general idea of an AT. We'll describe the detailed mechanism slightly later. What's nice about NAT is this: we don't need to ask the ISP for a block of IP addresses, which is very expensive. One is enough, save us lots of money. There are 3 more benefits, in fact, using NAT. One is this: if we want to change the IP address in the local network, we just change it. It's not like, we're changing the IP addresses of the gateway there, which is a global ISP, which is assigned by the ISP. Then we need to inform the ISP we're changing it to somewhere else. Otherwise, traffic is not going to flow through. Okay? But if we're just changing the local machine, then there's no need of informing the ISP. Nice, convenient, so save us time. Third benefit, well, if the ISP is not providing good enough service, we can actually switch to different ISP. And the IP addresses we have on the local machines, we don't have to reconfigure them. Yeah, we just stay using the same fake subnet address, fake IP addresses. The last benefit is slightly unexpected to many of you. Okay? Those devices inside the local network, those 10.0.0.1, 10.0.0.2, those IP addresses are fake ones. Packets originated from outside, from the internet, carrying destination 10.0.0.1 is not going to flow through the internet and reaching the gateway and therefore coming back to the host. Because the IP address of the gateway is what? 138 something. That's the real IP address. That is also what people call the global IP address. And that fake address there is the virtual address, the subnet address. Okay? So subnet or virtual address or fake IP addresses are not addressable. By not addressable is, what I meant is packets coming from originated from outside just have no way of reaching. Okay. So they are therefore not visible from the internet, not visible from hackers in the internet. So it's a security plus, okay, unexpectedly.
All right, so that was why we need NAT: to save money, to save time, and surprisingly, it's actually more secure. All right. There's a question, okay, what is the case that we want to change the address of the devices? Okay, so that is a very good question. Sometimes we might install new devices and the dynamic IP address that we have allocated to the local network, the address space might be too small. Then we might want to change that. In that case, we might need to change the addresses of all the devices that are using the same subnet. But IP address of NTU subnet, yeah. So, but back to the question from Tiandi. So, yeah, there will be occasionally that we want to change the addresses of the devices, such as if we want to change the block of IP addresses we use to DHCP the local devices. But that does not happen very frequently. Okay. And 140.112, that is NTU subnet. That is right, but it's also not exactly precise. 142.112 is an address block allocated to TANET. Okay, it's the Taiwan Academic Network. To be precise, NTU is only allocated part of the 140.112. Okay, so some of the 140.112 subnet IP addresses are assigned to other universities or maybe Academia Sinica, 中研院 within Taiwan. All right. But Weishan, that 140.112 IP address block, that is actually a global IP address block. Okay, So in the video, that example you saw, the 10.0.0. something, it's the local IP address block. Okay? And in case that IP address block is not sufficient for the local devices, okay, that might happen a lot in a, for example, a corporate, a small business network. Okay, good. I hope that addresses the questions. And some of you might be waiting, hey, exactly what is the mechanism of NAT? Here it is.
NAT's mechanism is quite straightforward. Only 3 steps, 1, 2, and 3. Step number 1, you heard about it a bit already. So this is to handle when packet is going out from the local NAT to the world. We'll have to replace the fake IP address with the real one. We'll also replace the source port number with a new port number. Okay, so the source IP address, the source port number, these 2 fields are replaced with these 2 values. And this pair, so 1, 2, 3, 4, okay, are also tracked, okay, being remembered in NAT's translation table. So the source IP and the source port number, as well as the translated source IP, source port number, will be maintained as a pair in the translation table. So when the remote host receiving this packet and sends back a response, in the destination IP address, it's going to be the real IP address, and it's going to be the new port number. So that packet coming into the local NAT, the NAT box there is going to look up the table and find the pair, right? So it's matching this IP address and matching this new port number, and therefore translate the IP address back to the corresponding port IP, source IP address, and translate the port number to the corresponding original source port number. And therefore, you see the destination fields is going to be replaced by the original IP and the original port number. And that packet then will travel the local network and reaching the destination. Let's use some animation to illustrate, it'll be easier to understand. So the local NAT here, using a fake subnet address. So this machine here, 10.0.0.1, is sending a packet to a web server, okay, outside of the local network, okay, inside the internet. The packet is going to look like this. Source IP being the fake IP. Source port number being the port the web browser is sitting on. Destination IP, the server's IP. Port number, the web server's port number. So that packet is going to reach the NAT box in the middle, and this is going to be replaced. This is going to be replaced. So 10.0.0.1 is going to be replaced by the real IP. And the 3345 port number is going to be replaced by a new port number generated by the NAT box here. Step 2, the NAT router there is going to add an entry into the translation table so that we know this old IP, this old port number is now being changed to this new IP and this new port number. When this packet reaches the web server sends back a response. Destination address will be the source of the request. Okay. So destination port, the source port number of the request. Now this packet will come back to the NAT box in the middle, and one more translation is going to be done. So this time, the process exactly is this. Let's look at the destination port number, and then go to the table. Look up the entry in the table such that the port number in the WAN part matches the destination port number. Now, destination IP address is definitely going to match the WAN side of IP address, because the WAN side IP address is going to be just 138.76.29.7. So this unique new port number is the key. So destination port number, you look up this value in the translation table. Identify the entry, and then replace the destination IP address with the LAN side address. Okay, port number also with the LAN side port number. And that's why we see destination IP address, now the fake IP. Port number, now the original browser's port number. That's how NAT works.
All right, so that's how it works. You map from the local address to the global address. And when the returning message comes back, you map from the global address back to the local address. Okay, that's a general idea. But the difference is that when the packet is going out, what you're mapping is the destination address. When the reply message comes back, what you're mapping is also the destination on the reply message, right? And by the way, to also show that the exact IP address range for NTU, Weishan, you see that NTU is assigned this block. Okay, so it's 140.112.42 dot something. Okay, and the block that that you ask, which is more general, it belongs to TANET, the Taiwan Academic Network. All right, good. Now, there's one more video. So we learned that the advantages of using NAT, right? Money, time, security. But are there disadvantages? There are, okay, quite a few.
Last are the drawbacks of NAT. Point number one, poor number, pretty short, 16 bits only. That is also saying we could have only up to 60,000 simultaneous connections. If the local network there is for home use, this is plenty. But if the local network there is for enterprise use, if a company is there trying to save money and subscribing to only one real IP address, having lots of employees, lots of machines inside, chances high the packets going for one flow might be mistaken, okay, with the other flows. Point number two, yeah, NAT is controversial. In the previous slides, you might see the authors of the textbook referring to these NAT devices as NAT routers. But routers are what? These devices in the core of the internet. Now, routers implement only 3 layers of protocol: physical, link layer, and network layer. So routers are also called the layer 3 protocols. Now, layer 3 protocol is supposedly only accessing layer 3 packet header. Layer 2 protocol accessing layer 2 packet header. NAT, if you think about the mechanism again, it's what? Replacing the IP address fields in the packet header. It's also replacing port number, okay, the port number fields in the packet header. IP address, yeah, that is a field in the, yeah, I know, layer 3 packet header. We learned about the IP packet format already. But port number, if you recall, in chapter 3, the transport layer, port numbers are there to differentiate different processes running on the host. It's actually a layer 4 notion. It's in the transport layer header, in the layer 4 header. So NAT as a router should not be doing that. So those who are against NAT boxes to address the network shortage, IP address shortage problem, okay, argue that we should probably, improve IPv4 such that we have more bits for the IP address field. So IPv6 is the next generation. It's using 128 bits for the IP address, much longer. We'll talk about this later. Point number 3, NetBox. Yeah, hosts sitting behind NetBox cannot be reached from a machine from outside. So that was actually presented as a benefit, a security benefit earlier, right? Hackers cannot be sending packets to 10.0.0.1 because that packet is just not going to go anywhere. Okay, not even reaching the NetBox in the middle, the IP address being 138. Something something. Right? Only packets with the destination address 138. Something something will be able to reach NetBox. Okay? And NetBox there, it will also not know, right, what port number, what local IP address to convert back to reach 10.0.0.1. So yeah, it's actually hard to reach local hosts from outside. So if packets are originated from outside, that's not going to work. Packets originated from inside, however, works. Now we know, right? So from 10.0.0.1, me, the box tracks the local IP address. Okay, keep it in a table. That packet gets translated using global IP, using real IP, goes out. Packet will come back to the router, and the NetBox look up the table and then translate back. So originated from inside, no problem. But data originated from outside, big problem. And this is a serious problem for these designers, P2P protocol designers. In P2P protocol, a lot of time we try to establish connections between one user's host to another user's host. You and me being hosts, we are, chances high, sitting behind the NetBox, sitting behind the net router. So we'll have trouble calling directly to each other, setting connection directly to each other. If you recall in Skype's protocol design, making a call, the designer of Skype actually take extra step. Okay? Bob and Alice, we need to call a relay peer. And the relay peer will exchange packets for each other, okay, for these two peers, for Alice and Bob. So application layer designer now need to worry, okay, in case layer 3 or layer 4 protocol is going to break. Okay, unexpected might happen. So one layer's protocol designer needs to worry about another layer's how it's designed, how it works. That's breaking the end-to-end argument. So by this here, okay, what I'm saying is this. The reference protocol stack there, okay, application, transport, network layer. So we say nice about building the network protocols and separate them by layers so that it's modular. Designer in one layer does not need to care about what's inside another layer. Exactly the same thing we are arguing here. Application layer protocol needs to worry about another layer's protocol, how it works. So that breaks the modularity there we have in the original reference stack. And that is what end-to-end argument is referring to.
All right, so those are the disadvantages. First is that the port number is limited, right? To allow the mapping, you need, if you want to have simultaneous connections, lots of them, then it cannot exceed 2 to the power of 16. The other two disadvantages, the second one is just saying that it's a little bit controversial. And IP address shortage is a level 3 problem, but we're actually changing also port numbers. And that seems to go one layer higher, covering both, changing information both in layer 4 and layer 3. Okay, controversial. Last one is actually very interesting. We see that one of the benefits is security, because then the machines outside of the NAT subnet will not be able to penetrate directly. But if this is a P2P application, right? The two peers are trying to call each other. If there's a net box, they won't be able to reach each other easily. Okay. Now, back to quiz 34. All right. So this is asking you to debate. Would you choose the ideal solution or the practical solution? I'm pretty sure that a lot of time that certain solution is ideal, the best, okay, that will fix the problem once for all, but it's not exactly practical. Given the resource, given the people who are involved, the ideal solution might be too large scale, too hard to achieve. So people turn to more practical solutions. So in a way, NAT there is more like a practical solution, trying to address the IPv4 address shortage problem. Okay, but there is another solution that is IPv6, okay, which uses 120-bit address space. So IPv4, 32 only, IPv6, 128. So that is actually a more sort of elegant and clean solution to the IP address shortage problem. Okay, so I'm asking you to debate within yourself or debate within the team. Which solution would you like? Would you rather, Q1, would you rather first pay for multiple IP addresses or use NAT? Okay, so this is also ideal versus practical, and why? Second, would you prefer using NAT versus IPv6? Again, practical versus ideal, okay, and why? Good. So find your teammate, go to the Slack workspace, W13 quiz 34, okay, and let's work on it. You have 5 to 8 minutes time. All right, so let's move on to the Slack space and see what you guys have here. So let's see, team 1 here. For private home use, using NAT is enough. However, if you are running a big company, okay, multiple IP will be better. Yeah, because you see that one of the disadvantages of using NAT is that the number of simultaneous connections you have is going to be limited. For Q2, you will prefer IPv6, okay, more direct and less problem. So you don't have the P2P application not being able to go through problem. Yeah. Let's see. Team 9. It depends on my pocket. Okay. Okay. When money permits, okay, I'll pay for my multiple IP addresses. Okay. Because then you don't have those issues with NAT. And there's no controversy either. For Q2, you will prefer IPv6. Yeah, because using NAT, again, you have the P2P issue. You have also the simultaneous connection being limited issue. Team 5? Yeah. So I think it seems that when it comes to your own pocket, then a practical solution is a little bit more preferred. Yeah. So budget dependent. For Q2, however, the general opinion seems to be IPv6 because then you don't have all these other issues. But you see also that using IPv6, you don't have that the security that NAT brings you. So I suppose that within your company or within your household, right, you would really like a general IPv6 use of IP addresses. But for like a cluster of your home network, cluster of your business where you would prefer having higher level of security, then you could add a NAT in front of that cluster, isn't it? And let's see, Team 13. NAT, yeah, because of money. And it's also quite easy to set up. I think every one of your household is using some sort of NAT. Okay. I'm actually not quite sure about the dormitory though. I think the dorms, depending on how large or small the dorm is, some might be using NAT. Again, when it comes to more general using versus choosing between version 6 or NAT, again, more of you prefer 6. For lab or household, NAT will be sufficient. Yeah, buying IP only when it's affordable. Again, IPv6. Okay, so last team, 14, we prefer 1 using NAT because less expensive and more secure. So very good. So team 14 mentioned that it's not only because of money, it's also because of security. So a little bit more consideration here. IPv6 because it solved the problem of IPv4 at the same time. Yeah, definitely. Okay. All right, so team 10 also. Solutions you provided very similar. People prefer NAT over IPv4, and people prefer IPv6 over using NAT. Okay, here team 6, NAT and IPv6. Good. Cheaper, safer. All right. And there was another question and a comment from Wei Shan. Can we have multiple layers of NAT? Okay, so that's a very good question. In fact, you may. Okay, but you see that in the end, the number of simultaneous connections allowed are still limited by the last layer, the outer layer of NAT. And things could get a little bit complicated. You see also that when the IP address need to be translated through the NAT box, it also takes some time. Okay, so I think using multiple layers of NAT, then you get, I think, much bigger IP addresses. You could accommodate a lot more devices. Okay, but then having multiple layers of NATs, then you also add a little bit of delay as the packet travels through the whole sequence of NAT boxes eventually to the devices back in the local network or out of the local networks. Yeah, Wei Xiang is very keen. Yeah, so 140.112.42, according to the page earlier here, yeah, it belongs to NTU, but it's not the only subnet that NTU owns. Okay, so there are actually more. So some of you might see 41 something IP addresses and so on and so forth. Yeah. So this is definitely too small for the entire university. And I think another question, what is counted as large dorm? Actually, I'm not quite sure. I know that some of the dorms are smaller. So maybe the subnet address allocated from Jizhong to that dorm is sufficient. But I think, I don't know. You guys might know better which dorm is bigger, having more users, having more devices. I think nowadays, very few dorms. So I think there's also previously 陆明馆, that's the dorm for professors or visiting professors. So that dorm, I think chances high that it's not using NAT back then, but I don't know. Okay, good. So I mean, hey, good question, Tanya. Yeah, you can actually find out what the dorm networks nowadays, okay, are operating with the NATs by default or not. Good. So that was NAT. We go on to the next topic. So what we have talked about so far, IPv4, and you've heard from quiz 34, there's a newer version, version 6. Let's first go over the motivation of IPv6. Why do we need version 6?
Last topic in 4.3, the IPv6. This is also the protocol some of these network engineers thought more legit, addressing the IP address shortage problem, instead of using these controversial net boxes. And that is why we actually upgrade from version 4 to version 6. The approach is very straightforward, expanding the 32-bit IP address space to 128 bits long. So the main goal of having IPv6 is exactly this. There are two secondary goals. First is to speed up the processing or forwarding of the packets as they come into a router. So in the data plane, packets coming in really, really fast. If we could reduce the forwarding time, processing time, we make the transmission process as efficient as possible. So you'll see in IPv6, the header is also changed to try to reduce the forwarding time, the processing time. The secondary purpose, this. We want to add something so that we could label the packets, so we could separate a group of packets from other, and make them flows, different flows. Now, with the different flows of these packets, we could then assign priority to a specific flow versus lower priority for other flows. Therefore, we could establish a more flexible levels of quality of service for these different flows. You see also header fields there to support labeling of flows, setting priority of the flows.
All right, so you see that essentially the motivation is because we run out of address space. So we extend the address space to 128 bits. Okay. Now, the next video is to tell exactly what changes are made and what the format of IPv6 is like. And pay attention, it's quite different from IPv4.
The IPv6 packet format. The header part of it is fixed size and 40 bytes long. Now, recall version 4. Is it fixed size or variable size? It's actually variable size because of the option fields there. So that field, in case we have more options, then it's going to go longer. No fields, 0. And therefore, IPv4 header size is 20 bytes minimum and could potentially be more. Now you probably recall, right, when we were talking about the IP header size, 20 bytes, we also mentioned the TCP header, 20 more bytes, together 40 bytes, just to store the control information. If we're sending a real message that's 10 bytes long, the entire packet will be this long, while only 10 of them is effectively sending data. This is very low utilization. So yeah, Poly kind of promised you that in the next version of IP, we're going to reduce the size of the header. But you see here, is 40 longer or 20? Yeah, 46 in fact has a longer header. But this is necessary, and this is as small, as short as possible already. Allow me to explain. In the IP packet header, there are two fields called the source IP and the destination IP. In version 4, the IP address space is only 4 bytes long. Now, to store source and destination IP, you only need 8 bytes. But in version 6, the main goal is to expand the IP address space. So unavoidably, we have very long IP address, and two of them, one for source IPs, another one for the destination IP, together 32 bytes. If you look at this, version 6 header 40 bytes, so we have only 8 bytes for the additional fields. While in version 4, 20 bytes long, we have 12 bytes for the additional fields. So the designer of IPv6, you see, try very hard to reduce these other unnecessary part of the header, removing them away, removing these fields away from the header. Okay. So 40 here, longer indeed, but it is actually after we try very hard making the header part as compact as possible, as small as possible. In fact, the second feature of the version 4 header is this. To recall, in the fragmentation and reassembly function of IPv6, we have these 3 fields in a row. ID, fragmentation flag, and offset. This row of extra header fields remove entirely, okay? And this is done by disabling the fragmentation and reassembly function in version 4. So in IPv6, no longer allowing fragmentation. And this is why we see version 4 header, although longer, it looks really clean and compact. Okay. First, the source address. Second, destination address. And the rest is only just 6 more. 1, 2, 3, 4, 5, 6. First here is the payload length. If you recall in version 4, we do have what? The header length and the entire packet length. Because the header size can vary. And the packet size, because the data size can also be different, so we need 2 lengths. Here now, having a fixed packet header size, we need just the payload part, okay, the payload length to indicate the size of the data down here. Hop limit, this is just the TTL field, okay, just like in IPv4. Next header, it looks odd, we've never seen this before, but this is really the upper layer field in version 4. So what it does is, once we extract the payload, we actually forward the payload to what's indicated by this pointer here. And so further processing will be done using this handler on the payload. The version field. We also have this in version 4. So the only difference is that this value will always be 6 in version 6. Priority and flow label. These two are new. So flow label here is to allowing us to group a specific set of packets together. Okay, so coming from one application, coming from one service, they could be carrying flow ID 1, and other packets from other services, flow ID 2. So we could identify packets for one flow, okay, and packets for yet another flow. So we could separate these packets traveling the internet. As a result, we could then provide different priorities to different flows. So some flows will go earlier than the others. Therefore, we provide flexible levels of these QoS. Now, there are some more fields we remove, okay, not just the fragmentation fields. The header checksum in IPv4 header, that is removed because to calculate checksum takes time. To check the checksum takes also time. So let's try to reduce the forwarding processing time as much as we can. So let's remove the checksum part. Yeah, and take the risk of some bits in the header being flipped. Yeah, we might have some, might run into some errors, but chance is very low. Okay. Yeah, we way higher here, way more here, trying to make sure the forwarding part is fast. And we move the option part down to the payload, so that when we grab the payload and give it to the handler is going to look at the first few lines in the payload, and those will contain the options. Okay. Yeah, there's one more thing. Yeah, ICMP version 6. What is ICMP? You need to think back. In one of the earlier overview slides, I was talking about the functions and protocols implemented in the network layer. Right? In the data plane, we have forwarding. In the control plane, we have routing and management. ICMP is one of these protocols implementing the management function. Okay. So we also extend the version for ICMP to version 6. Okay. And the reason we need the version 6 ICMP is so that we could send a special message, packet too big. Okay. Allow me to elaborate. Now we don't have fragmentation and reassembly, but the fact that some of the links on the internet allows smaller MTU is still there. So what if we have big datagram coming to a router and the next link is saying MTU smaller, but we cannot fragment this datagram anymore? What should the router do? What can the router do? Okay, so the mechanism in version 6 is to send a special message, an ICMP version 6 message, back to the data source saying packet too big and the better packet size is below this MTU value. Okay, so there's additional message being defined in ICMP version 6, allowing the routers to manage themselves, deciding what is the best datagram size. And we'll just ignore this part. Multicast, we'll just not talk about it at all. Okay, it's a can of worms. So this is IPv6 packet format.
All right, so that was all the time we have. Perfect timing. And so if you have further questions, feel free to type it down on the chat. Otherwise, I see you tomorrow morning. Okay, bye. Oops, sorry. Music.